Think about a structure that stayed the tallest man-made object on Earth for nearly the entire span of recorded human history. I'm talking about the Great Pyramid of Giza, a colossal puzzle made of 2.3 million stone blocks. If you look at the surfaces closely, you can actually see the ghosts of the process. Those little chisel marks from human hands are still scarred into the stone. Some of these blocks aren't just heavy, they're monolithic, with some hitting 50 metric tons. But the real paradox, the part that really gets you, is the precision. The four faces of the monument are aligned to the cardinal directions with an accuracy that's almost impossible. And that's despite the fact that the magnetic compass hadn't even been invented yet. It wouldn't be around for another 2,000 years. Now, how did a society do this without digital blueprints or power tools? Today, we're going to dismantle the mechanics of how millions of tons of rock were positioned with millimetric precision. If you're standing on the Giza Plateau today, the scale of the monument is almost impossible to process until you actually look at the ground. The base of the structure covers an area roughly the size of 7 New York City blocks. And it's not just a massive footprint, it's one of the most mathematically precise surfaces ever created. The foundation is almost perfectly level, never deviating by more than an inch across its entire expanse. Now, if you were to walk the perimeter, you would find a level of accuracy that feels, well, anachronistic for a culture that only had copper tools. This physical foundation was the critical starting point. It provided the stable, flat platform needed to support the weight of millions of tons of stone without the whole thing shifting or leaning as it climbed toward the sky. Beyond the sheer physical scale, the central mystery is the management. The lineage of knowledge began with Sneferu, Khufu's father, the pharaoh who essentially taught Egypt how to master the geometry of the pyramid. But the actual design and execution were steered by Hemiunu, Khufu's half-brother. As the royal architect, Hemiunu had a very specific, almost aggressive timeline. He was aiming to complete the entire project within 20 years. To meet a deadline like that, the logistics of the workforce were just staggering. The site required up to 25,000 builders, which was a significant slice of Egypt's total population of about 1 million. Now, this wasn't a disorganized mass of slaves, as Hollywood often suggests. It was a highly stratified professional system. You had 20,000 people dedicated to moving stone, and another 5,000 providing the specialized food, medical care, and administrative support. The project basically became a massive exercise in state bureaucracy. Hemiunu transformed the construction site into a high-stakes engineering campus, where laborers were fed prime beef and organized into competing crews to maximize efficiency. If we look past the limestone shell, the interior layout reveals a complex series of corridors and voids. The design incorporated 3 distinct burial chambers, each with its own access passage. Now, this wasn't a matter of luxury, but a strategy for risk management. The first chamber was carved underground, serving as a temporary solution in case Khufu died early in the construction process. As the project scaled upward, the architects added a second chamber, though this one was hidden behind a false wall to mislead tomb robbers. They were fighting a war against looters from the moment the first stone was laid. Finally, we reached the third and highest chamber. This is the most ambitious section of the layout, accessed via the Grand Gallery. And this is no simple hallway. It's a soaring corridor with corbelled ceilings, a technical feat where each layer of stone slightly overlaps the one below it. This design distributes the crushing weight of the pyramid above, turning the passage into a high-precision arterial system carved into the heart of the mountain. Deep within the structure lies the King's Chamber, a space that represents the absolute zenith of Egyptian masonry. Unlike the rest of the monument, this room was constructed entirely from pink granite monoliths. These stones weren't local. They were quarried from Aswan, meaning they had to be transported over 800 kilometers, roughly the distance from Cairo to the border of Sudan, to reach Giza. When you examine how these blocks are joined, the precision is just haunting. The granite monoliths were fitted together so tightly that you can't even slide a razor blade between them. This isn't just a tight fit, it's a level of accuracy that challenges our understanding of Copper Age tools. You're looking at blocks weighing several tons, each polished and squared with such exactness that the seams effectively vanish. Today, the monument appears as a stepped, rugged fortress of weathered stone, but 4,500 years ago, it would have been blindingly bright. The structure was encased in smooth, white Tura limestone, which reflected the sun's rays with a mirrored finish. At the very peak, the monument was topped with a golden capstone, known as a pyramidion. This final piece acted as an architectural crown, locking in the symmetry of the entire mass. This white casing was more than an aesthetic choice. It functioned as a structural seal, transforming the rugged core into a type, object, properties, result, type, string, required, result. Single, seamless unit of light that could be seen from miles away. To understand how these massive stones were moved, we must look at the environment. The Nile's annual overflow provided the rich topsoil that fueled the entire operation. By producing a massive surplus of crops, the state could sustain a standing army of specialized laborers during the flood season, when farming was impossible. As for the physics of the haul, moving a 2-ton block up a slope requires a team of approximately 12 workers. It's a brutal, calculated process of friction and force. Engineers have determined that an 8% incline is the absolute limit for average workers to move these blocks efficiently. Anything steeper, and the team would lose their grip or the block would slide backward. This means the Giza Plateau was not just a construction site, but a carefully engineered grid of ramps and angles, where every single movement was a calculated logistical achievement. How did these blocks reach the summit? The traditional explanation is the external ramp theory, suggesting blocks were dragged up a ramp that grew and extended as the pyramid rose. In this model, the ramps were built into the structure and filled in as the project advanced. However, this creates a geometric paradox. The faces of the pyramid must be maintained at precisely 51.9 degrees. A single straight ramp reaching the top would have to be over a mile long to maintain a workable grade, a distance that would require as much material as the pyramid itself. To solve this, some propose a corkscrew ramp that spirals around the exterior, eventually becoming part of the walls. But a more modern approach comes from Jean-Pierre Houdin. He proposes a hybrid system. An external ramp was used only for the first 60 meters. According to Houdin, this ramp was composed of limestone blocks that were later integrated into the upper layers, allowing the builders to maintain the precise angle of the faces while still moving massive weight upward. But how did those massive granite beams reach the height of the king's chamber? Houdin proposes a mechanical solution. He suggests the Grand Gallery was not a ceremonial passage, but a functional counterweight system. Think of it as a prehistoric elevator. In this theory, the stone benches lining the sides of the gallery acted as rails for carts on wooden rollers. These carts, weighted with heavy stones, would slide down the slope, using gravity to pull the granite beams upward via a system of ropes. It's a precise application of physics that turns a steep corridor into a heavy lifting machine. By utilizing the interior of the structure in this way, the Egyptians could have moved their heaviest materials without needing a ramp that extended for miles across the plateau. The Great Pyramid stands as a testament to a time when human organization was the most powerful tool available. From the 800-kilometer journey of the Aswan granite to the 8% incline of the hauling ramps, every detail was a calculation. We see a society that didn't just move stone, but mastered the mathematics of weight and friction. While we may never find the original blueprints, the structure itself is the blueprint. It leaves us with a lingering question. If a civilization with copper tools and rope could achieve millimetric precision on a scale of 7 city blocks, what other capabilities did they possess that we have simply forgotten? The stones remain silent, but the geometry continues to speak.